Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good afternoon. I'm Dennis Gannon, part of the Microsoft team here. I have a question, actually. I'm curious of the group here, how many of you are PhD students or students? How many students? Oh, good group of them. I was very impressed, by the way, by the student presentations that we saw just before lunch. You're doing some very good projects. And how many are like university or professors or researchers? Oh, that's about the other half. This talk, thank you, good. This talk, I'm going to go basically give you an overview of what we have been doing with the Azure cloud. First of all, I'll tell you about what the Azure cloud really is, how it's built, and then I'm going to give you an overview of just a few of the science projects that we have done around the world, just so to give you a sense of what's possible. So, first thing is I need to make this thing, there we go. All right, Tony Hay already gave you this slide. The data explosion is transforming everything. Every field of research is now a data science field. And the other thing that he already told you is this, that this is causing this fundamental change in research, and that fundamental change is what we call the fourth paradigm, which I think you've probably heard 10 times already at this meeting. Only three, okay. I'll say it 2, 3, or 4 more times before I finish. All right, now what I want to do is to get into something that Tony did not talk about, and that is what is the Azure cloud, because a number of you use it, or I hope a number of you will want to use it. First of all, it's based on these data centers that we have. These are very, very big facilities. They use enormous amounts of power. And each one of these facilities, the really big facilities that I've listed here, those are the current ones. There are more coming in various places, and we hope to see some come in the places where you don't see them right now. We hope that'll happen. So each one of these big facilities is on the order of, let's say, 500,000 servers. So they're very, very big. Plus we have a lot of other smaller facilities, that maybe 100 other what we call edge facilities, or smaller facilities around the globe. Now, how are these things constructed? Let me show you. So we go through these generations. There's a history of how to build these large data centers that goes back 10, 15 years. The early ones, the very earliest big data centers were just traditional servers. You buy just traditional boxes of desktop machines, and you throw away the keyboard and the monitor, and you stack them up, and you wire them together. And that was really the early days of doing this stuff. That was sort of the first generation of cloud facilities, of data centers. You know, there was an enormous problem with that approach, because after all, you buy these big desktop machines, you get a very large pile of styrofoam after a while, and what do you do with that? That's a problem. So the next thing was to basically build them in large racks, to increase the density. So just put them in racks, buy racks, get small servers, flat servers, and stack them up. Then another thing happened as we were populating racks, and our competitors at Google and Amazon and these other interesting places building large data centers started to ask the question, how, we buy the racks, we buy the servers, we put them in. Can't we just buy the racks with the servers already in them and come as a big package? And someone at one of the companies that was supplying these racks and servers said, well, yeah, we could do that. We could put them in a big package. And the idea was, the question was asked, how big a package can we actually build? And someone said, well, whatever it is, it has to fit into a shipping container. And that gave birth to a whole new industry, which were giant, basically standard shipping containers filled with lots and lots of servers. Now, at each step, and so then you can take a shipping container, move it into your giant building, set it down, and it would be already configured. It'd have the network in it. It would have, all set, ready to go. The buildings that these things were coming in were getting to be a very big problem because they were getting bigger and bigger and bigger. They're the size of 10 major football fields in size, and they're 2 stories usually. So they're very big. They require massive amounts of air conditioning. They're not, and also backup power is a huge problem for these facilities. So the last generation, or what we call our current generation, or Generation 4, we took a look at these big buildings and said, do we really need the building? Our servers are already coming in containers. Do we have to put them in a building? Can't we figure out a better way to do it? And that created something new that we call an IT pack. Now what this is, and I've got another picture, is a very specialized type of container that we designed at Microsoft. And what it is you have, inside the container, you have racks with several thousand servers inside one container. And it's designed, those of you that, how many people here know about hot aisle, cold aisle data? Yeah, some people do, yeah. And so basically you have the cold aisle here, the hot aisle here, air comes in, the one whole wall of the container allows air to come in. This is all ambient air cooled. So there's no cooling apparatus. There is a bit of water cooling, but instead of a big pipes that we had before, it's a small, what we call in the US a garden hose, something that you use to water your tomatoes. It's very simple. And that's the level of water cooling required. Otherwise, and it only comes on in really hot environments, because this is to be placed with no building in any environment. It has 3 connections. It has a little place for your water hose. It has the network connection and the power, and that's all. And so this thing is very self-contained. It senses by changing these louver connections on the side, you can change the different amounts of airflow inside. You monitor, all the systems are constantly monitored in the system so it can actually work. So to show you that this is really real, there's a picture of one of them arriving on a flatbed truck, ready to be installed. So they just simply, the truck rolls in, you pick up this thing with several thousand servers in it, and then you put it down, and then you assemble these into this framework here. So this shows you an actual data center. There is no building anymore. The IT pack is this thing underneath. To be honest, I don't know what the thing on top is. It is not air conditioning, but it's some sort of thing they have to have. I don't know what it is. But this is one of the new data centers. So that's all there is to it. No big buildings anymore. Now, we're not alone in doing that, but it is something that we're pretty excited about. It allows us to reduce the power consumption, because these things are very power hungry. And one of the advantages of building a data center that has millions of servers in it is that you could exploit economy of scale. That means lots of servers where you manage the power across the entire collection of servers in the most efficient way possible. You have a cooling system that is incredibly efficient. It's ambient air. It doesn't require big generators. We get away from backup batteries and fancy generating systems by software now, which means that if something fails, we can automatically transfer load from one thing to another. So it's more decoupled. And this is very important capability. So that's how these data centers are built. Like I say, we're looking at a variety of different ways of providing the electrical power. Geothermal is one thing that we're looking at. There's one experiment that's been reported on in the press, so it's no longer a secret, I don't think it ever was actually, of using, putting the data centers next to very large garbage places where there's lots of generated heat and gas that you can then recycle into electricity for the system. All right, now I'm going to change gears and I'm going to talk now about what we've done for science in the cloud. And so I'm just going to give a series of examples now. So we started this project about 2.5 years ago when Azure was still young, and we started giving away pieces of Azure to the research community. And I was working mostly with the science funding agencies. So I went in the US to the National Science Foundation and I said, hey, if you have researchers that want to do cloud stuff, I'll give you a big chunk of my cloud, and then you could give it to your favorite researchers. And then they said, yeah, it's great. And we'll also give them some money to actually do something with. And then we went to the European Commission, had a good project there, been around the world doing this. So now I got 90 projects altogether. Actually, that's growing, probably hit 100 soon. And of those projects, some of them were really turned out very, very well. Some of them didn't. You know, this was the sort of thing you're experimenting with. You don't know what sort of science will work in the cloud. One thing that does not work very well in most cloud environments are the applications that are designed for very high-end, tightly coupled supercomputers. There's a big architectural difference between these data centers and a fancy supercomputer system. And I can go into that in a question and answer if you want me to. So, for example, some of the projects we started, one is one around protein folding that we did with the University of Washington, where we used 2,000 servers over a 5-day period to do some protein folding having to do with a particular structure of protein that Salmonella uses to inject DNA into its victim. And that was actually really nice. It generated some nice articles in Science. Another one I'll talk about is the fire protection thing that Tony already mentioned. I'll talk about that later. A project in Australia was looking at using a lot of Azure cycles to do computations having to do with magnetotellurics, which is a type of, it has to do with discovering minerals underground, which is something in Australia that they actually care about. In France, the Institute INRIA, which is the major computer science research institute, did a really cool thing involving looking at brain scans, fMRI images, and genetics as a big data challenge. Lots of MapReduce computations to understand the connection between certain genetic SNPs and the occurrence of brain tumors. And that work is still going on. In Japan, we had a really great project on looking at Japanese natural language analysis and structure. So those are a few. Let me give you some more. And in Europe, we started with 7 pilot projects, and these were very, very interesting. And so I would go through some of these. One was to really look at, basically looking at large-scale structures, such as architectures would design. So this is professional architectures and civil engineers built some tools for modeling their sort of 3-dimensional test cases of what a physical structure would look like. Another one was, this was a company, this was very interesting, it's a company called Green Prefab in Italy. It's a startup company. Started in a university. I was funding university projects. They got going and then they became a company. And they were looking at ways to create architectural renderings for buildings for green construction. Let's see, another project was looking at the distribution of species in a variety of places, occurrences as relation to environmental conditions. Then we have the Greek fire one, which I'll skip for now. Bioinformatics tool. We had a lot of success with bioinformatics tools, and I noticed that there's a number of the projects here related to bioinformatics. Another one having to do with systems biology, as distinct from, say, genomics. And another project having to do with drugs discovery. So these were our 7 pilots in Europe. After those 7 pilots, we went on to another, I think, about 20 or so additional projects after we got these first pilots done. So that was very satisfying. Now, the one, again, I don't have to talk about it because Tony Hay already mentioned this. This was this one in Greece. And it was really interesting because it started a university project, and they really were looking at the idea of dealing with crisis, dealing with getting data together from a lot of different sources. I mean, they have sensors on all the fire trucks. I think they have sensors on all the firefighting personnel. They've got sensors around in the forest on the island that are measuring things like humidity and heat. They've got the weather prediction stuff. Bring all that data into the cloud and integrate it. And then what the cool thing really is they did this in a way in which it could be used by the actual firefighters. And so they deployed this in places where the firefighters could actually get at it. They could communicate, they could look. You know, I don't know if they got as far. I know they're working on this so that the firefighters in the field could actually look on a phone if they've got phone connections, and they could sort of see the map of what's going on, ask queries. Now, this was an example. Firefighters using this result of cloud science that was very, very significant to me, because I very strongly believe that something that we have to do is to let scientists be scientists. The people in this room, you're all adventurous. You're adventurers. You're willing to try crazy things and do programming and complicated scientific endeavors. Most scientists don't want to do that. They don't want to program supercomputers. Most scientists don't want to program a cloud. What they want to do is get their science done. And just like the firefighters, they need to fight a fire. They don't want to have to stop and write a bunch of Java code in the middle of fighting a fire to get something done. They need to fight the fire. Scientists need to get their work done. And what do scientists do? They use standard tools. They use spreadsheets, statistical packages. If they do any programming at all, it's usually modifying some parameters in an R package. And so a lot of the tools that the Microsoft people have been showing you are really about helping this long tail of science, this community that they need to be able to do their science better, but they're going to leave it to people like you to do the hard part, to figure out how to make it better. And so, you know, here's another view of this. We want to bring the cloud to the desktop. That's something that we feel fairly strongly about. 5 minutes, perfect. Now, one of the things that we've been doing on this is, well, let me just say through this. So we need to, and you've heard this message already several times, data sharing in the cloud. They need to sample and manipulate data, tap data analysis algorithms, invoke analytic models, do machine learning, and publish data and do visualizations. So we've been working on a number of things, and you've seen some of these, so I can skip through them. One that I've been working on with some other people is creating, a lot of the scientists I know build really incredible tools using Python. Any Python programmers here? There's a few, yeah. So what we've done is we have put first-class support for Python on the Azure cloud. So if you're a Python programmer, we can do Python really well. There's something called the Python Notebook, which is a really great way, interactive way of running Python applications on the cloud. It gives you a way to type in your code, your Python code, and execute it and get the visualizations directly. So you're sitting on your laptop, but the computation is running in the cloud to do your Python work. Now we have other applications that you've already heard about in the last session. You've heard about World Wide Web and Layerscape, Chronozoom, and Fetch Climate. So these are the types of tools that we're trying to get out. And these are tools connected to the cloud. They depend upon the cloud, but they're designed to help the scientists do their science. So, you know, in the future, I think there's a number of interesting new horizons for science and places we can go. And I'm going to skip some slides here and get to this last slide, which I think the most important thing we can do is to help democratize research. Today, the majority of researchers don't have access to big computing, but tomorrow we think that they will, and they will have access through these applications in the cloud. So I know I'm out of time there, and we've got 2 more really good talks coming up.
Okay, thank you very much, Dennis.
And I'll be around after the thing and around tomorrow in case anybody wants to talk to me.
Well, we do have a couple. We have time for a little bit, a couple of questions. If folks have some questions they'd like to ask. Oh.
Hi. My name is Munir Skaf. I'm from the University of Campinas, and I am a theoretical chemist. I do molecular dynamic simulations of proteins. Just one of the applications that you've shown. In my group, we have built the first stage. We put up, a few tens of desktops, and we built our own clusters, and then we dropped that and we purchased a rack. But now my chairman is complaining that I'm using too much energy and too much air conditioning. So I want to drop that and go to the next stage. But I want to be a scientist, and I don't want to build one data center. So can I buy time at the Microsoft Cloud? Can I get time for free?
We're in the business, and that's a very nice thing to hear. When someone says, can I buy something? Yes, you certainly can. But we could maybe work together to do something more interesting. So we could talk about that after.
All right, thank you.
Actually, I have a question for you, Dennis. You mentioned that some of the projects were more successful than others. And I won't ask you what the statistic was, even though Professor Brito gave us some examples of what their percentages were. But I'm curious, what actually do you use to measure success? Is it that because the problems are embarrassingly parallel, or is it some other factor?
So actually, measuring success is really, well, I could tell you the statistics. Actually, I consider about 30% of them to be very successful. And the way I measure success is that finally, is there a result that is something running in the cloud that the researcher is actually able to, in most cases, these were scientists that wanted to do more science. And if they are begging me to use more and more cloud because they're getting closer to their scientific goals, and their students are all using the same platform, if they built something that they can reuse and they're using it, that was my sense of success.
Oh, that's excellent. Okay, well, let's thank Dennis one more time. Our next speaker is Marta Matoso, and she's going to actually be talking to us on I have to take a look here, user steering and workflows.
Okay, hello everyone. I'm very happy to be here and part of this exciting workshop. We also have a Brazilian eScience workshop that I started with Jeff João from here, from USP. And it's very nice to have this opportunity here. So we've seen many topics very interesting in eScience challenges. I'm going to talk to one specific that involves cloud, but also high-performance computing workflows, which is related to the participation of the user during the workflow execution, long-time running workflows. So this is the agenda. I'll talk a little bit about the life cycle of the workflow and then the challenges on user steering. So this is a generic, actually it's a real workflow of one of the users that we work with. Also related to the trypanosoma cruzi problem that Christina mentioned earlier with the leishmania and drug investigation. The idea here is to show that initially many workflows work this way, but you collect data, you do some analysis on your desktop, and then you evaluate long-running programs in the cloud or in a high-performance computing center, and then you analyze data. If you have a workflow management system behind this, it actually can follow the execution from all these areas and collect provenance. My point here is related to the time that the workflow spent here, or the programs that are executing here. And Rob already mentioned the problem of a batch experience, waiting for a long time for it to finish here and only do the analysis later and you realize that it's wrong. So we are working on issues of improving this part of the steering, the long-running tasks. Not just following what has been going on, but also being able to interfere on this execution and save some time. So the workflow execution life cycle actually has, well, many phases, but in a general way, it could be seen as a data planning, execution, and analysis. We've seen a lot of very nice tools on the tutorials and on the talks about how do you select the data, you do the data planning, and also to use visualization and provenance to do a very nice analysis here. So I'm going to talk some more of this part. Let's see an example of a long-running workflow where you have to combine a lot of parameters, different values, analyze different algorithms. If you have to work in a batch mode, such a way of speaking, just to follow Rob's term, you have to plan in advance all the evaluations you want to do. And then you write a script, and then the workflow execution engine will follow that and give you all the nice provenance that you can see during the workflow execution. But what if you would like to change some of that during the execution, not just interrupt? So these are, there are some issues there. So here are a few of some nice tools. Some of them I'm very familiar with. And some of them are very good in high performance, scalability, and they all share the good thing that is collecting provenance. But what happens in most, well, in all of these systems, as far as I could see, is that provenance is only available for querying after the workflow has finished. You can follow what's going on, you can see each step of the execution, but you cannot really submit a query and search for a specific data or a specific part of what's been going on there. So following that batch mode kind of working, the workflow spends a long time here executing. And then when you realize it's not exactly the way you wanted, then you go back and change the parameters, change the combinations, and go all over again. And so our users would like to do some changes there. What happens is once they start using the workflow systems, they get very excited about the provenance, about the way it's doing very fast, about the way they don't have to buy a supercomputer, they can run it on the cloud. And then they start wanting for more. And so what our users have asked us was to do some interference. I'd like to query inside data during the execution and interfere on the execution. So I was very lucky to see the exhibition on Matisse called Pairs and Series. So he works in parallel. He does the same painting parallel using different views. And the nice thing, one of the things that reminded me about the scientists I work with was the script. You know, he does a script following, determining all the colors that, well, there's a sketch and all the colors that need to be used, the texture, the styles, and all of that. And of course, during the course of the painting, several changes are made. So it's not like, you know, you follow that and then you get to this very nice picture. In fact, several stages are going on. But these stages are not fixed. It's not like he is looking at each stage and deciding and waiting to the end, just following the script. What happens is that he changes the color in the middle of the execution, does other changes, and that's actually what is kind of happening. You know, being able to follow step by step of the workflow execution is very nice. But an interesting thing would be to change the script. If the script of the workflow is hard-coded and it's very hard to change it and do interference and continue to have a consistent execution. So these are one of the challenges of doing these runtime changes and dynamic workflows. So basically we can divide the workflow systems like the offline and the online. So the offline is the batch mode where you run and wait for the result, and the best you can do is if you see something is not going wrong, if you open your files and do an interference, then you can interrupt and start all over again. And an online dynamic workflow execution would be having access to query provenance, having access to evaluate partial data, fine-tune parameters, occasionally visualize the partial results that are being generated in this very long-running execution, and also skip some parameter combinations is also something that we have been asked for. So we are not inventing this problem. In 2006, many scientists gathered to discuss. Carol Goebel was one present at this meeting, and they came up with a very nice paper on this challenge, and several of them have become true. So scheduling, high performance, these challenges are taken care of. But this part of the dynamic workflows is still kind of open. So there are many interesting problems to work with in this area. So here are some examples of real users, real applications that our group has been working with using high-performance scientific workflow support. So in the bioinformatics, the evolutionary studies and drug research, they like to query the provenance and see if the results are having a bad quality, if the filter, the e-value similarity parameter needs to be adjusted due to the characteristics of the data that is being analyzed. In the oil and gas, they do large parameter exploration, for example, to analyze the structural properties of these risers that connect to the platform to the bottom of the ocean. They have 2,000 meters long. So they use extreme conditions and analyze its behavior to predict how it's going to behave. But sometimes, you know, the combination of parameters could benefit of a branch and bound technique. You know, based on this parameter, this is fine. I don't need to evaluate all the rest. And they would like to have access to that slice of the parameter space and maybe do a visualization of that slice, of these characteristics. So combining these things is very important. And some of the tools we saw in the tutorials, they can do that. But as far as I could see, the user would have to wait for the workflow to finish and do that. So doing this in runtime is just a matter of having provenance available and related, for example. But jumping pruning a slice of the parameter space, that's kind of more complicated. Another group that we work with also in the oil and gas area is the structural engineers, mechanical engineers, where they run solvers and do numerical simulations, also to analyze the relation of fluid structures down in the ocean. And they are applying uncertainty quantification models to improve the numerical analysis and predict the behavior of this interaction. And once they started using our workflow high-performance solutions, they realized that by querying provenance, they could interfere and adapt the uncertainty quantification progress, you know, the way it's going towards the best result, or the convergence or the error. Sometimes before it reaches what the original algorithm would do, by querying provenance, they know it, I'm fine here, and then improve the result. So these are like a summary of some challenges and the potential of things that you could do, and some of the issues involved. So The first part is somehow a bit easier because user steering, you just have to make data available during the execution so that the user can analyze. But it has to be nicely related so that you can browse and go to wherever you'd like to, having access to the slides, the specific slides. Runtime steering and interfering, having a dynamic workflow, there you have more challenges, but it's still many things that are possible to be done. So fine-tuning these solvers and being able to take advantage of the first part that has been executed, because usually they run several steps, several programs. So having that context kind of in advance and just changing the following is something that they are finding very useful. So changing the tolerance, some solver options, and the stopping criteria. Why it's hard kind of find this type of interactive and user steering? Well, I mentioned most of the time provenance is being collected in logs and only available for querying at the end of the workflow. So one way of dealing with it is to already store provenance in a queryable format or a database system in our case. And then you could store not only the definition of the workflow that's going to be executed, but the files it's going to access. If this is all structure, you can kind of relate things. Another difficulty is that sometimes, most of the times, the user submits the workflow from the desktop. Sometimes the initial running and executions are done locally and the other goes there. So the provenance gatherer has to keep following what has been going on to collect provenance. But this is not a problem as long as it's all interacted and integrated in a not necessarily centralized database. So this is querying, and here I'm going to show an example of a kind of interference, a way you could represent this change on the iteration and all that. So if you have a flexible script to run your workflow, parameterize it, where you can replace some things. Maybe you could, at the beginning there, we have the data files that are going to be used, some tests, some programs that are going to be executed to run the workflow, and then you check the error and go back again, and so on. So if during the course of this execution, the user here is able to submit a query to the provenance database, and then decide to change or interfere because she couldn't plan in advance all the possible situations, all the combinations. It's not just looking at the error. They actually analyze other data and other characteristics to interfere there. So by having some checkpoints and some notices that you can receive during the execution, you can take a look and decide to change. You know, these workflows are long running. They take hours, days, sometimes weeks. The user is not going to sit in the desktop and wait until the end, or we had some difficulties in some tools that the client of the workflow management system had to be on, the server on for the long duration. You know, you have to do in a kind of remote way, but still connected and on some specific parts. So having a checkpoint is not a difficult thing. Sending a notice through Twitter or wherever is also possible. And then submitting queries to the provenance database at the cloud. And having an analysis of what is possible to do in that way. You can do the changes, submit, I would like to change this, for example. If we want to classify kind of the issues that are related and involved in this kind of support, we could say workflow execution monitoring, data analysis at runtime, and dynamic interference in the execution. And each one of the steps has its own challenges and necessary tools to combine with. We are going to present a paper in the SIGMOD workshop next month where we analyzed current solutions in details. And so I'm not going to discuss on all of them. You could have a look at the paper, but the important thing is there are a lot of open issues. Most part hasn't been, we haven't found enough information for this support kind of. So the dynamic monitoring is the problems we are working now, and we have been working in last years. And they could be divided into simple interventions and more complex interventions. So these are some approaches. Blah, blah. Well, so here is our approach. I'd just like to point one issue that we think it's an interesting part of the approach. Is to have an algebraic approach. I'm from the database area, so I love relational algebra and structuring data and having organized things in data view. So we have this algebraic engine, and all the script that's going to be executed is structured in data, like in relations and operations that work in the relation. We don't put the code of the user inside the database. We don't change the binary data and the local code into text or whatever, but we put metadata in the database style, and we define the workflow in an algebraic way. And in this way, since it's all structured, it's like we are running an interpretive workflow execution engine, and it's not that hard to change things during the workflow execution. And in addition to that, the user can query, and we can use Provenance to improve our scheduling algorithms, our fault tolerance algorithms, because we have not only access to runtime, but the kind of behavior that these systems have. So we have been using that on the cluster, on the cloud, and we are taking a lot of advantage of this very special knowledge that Provenance can give you at runtime to do adaptive executions and this kind of thing. So we have experimented for this kind of parallelism is quite simple. It's like the Hadoop, the map in Hadoop. You know, you just have to run the same workflow for that different combination of parameters. The problem is balancing and taking care of all that. And if you take a Hadoop, a plain Hadoop approach, what we have seen that in this kind of application, it doesn't have adaptabilities. It will predefine, I'm going to use a large-scale machines, and I'm going to use 11 machines, and that's it. It's going to run until the end, no provenance. Whereas in this kind of approach, if Hadoop had this algebraic approach, and then, you know, the pig algebra, when it's mapped to Hadoop, they forget about that, and they follow that script. So maybe using an algebraic approach, using a provenance would do a lot to this kind of. Do I still have time? Okay, so this is just a nice picture of one of the things we have been doing with our bioinformatic users. We presented a poster last year in the supercomputing conference. So the idea is that in this lightning here, you know, the workflow passes by a checkpoint, and the user gets an SMS or whatever, and then starts submitting a query, and then with this table, she analyzes what's going on and say, I'm going to stage out this partial result and see how my phylogenetic tree is behaving, and then brings it back, uses visualization tools and tile wall display and all these many high-tech things. And our engines are there controlling what's going on and heavily based on provenance. So I'll skip that. And I really wanted to talk about this, but unfortunately, because Drew talked so much about inverse problems, about uncertainty and predictions. And these users that use uncertainty quantification on solvers, they are very excited with the using of workflows and all that. So we have some papers. Okay. So in this case, they are trying to. I've put a picture of a submarine, which is easier to see, but in fact, they are interested in the deep oil platforms and in the fluid dynamic structure. So here they are analyzing the turbulence and of this moving object that is also happens in real life. And so they have a parallel solver with the parallel solver is here. A lot of steps. They generate billions of meshes to solve with finite elements. And all of this is part of the uncertainty quantification process where they want to predict what's going to happen and how the resistance of the materials and this kind of thing. So they have some samples, and in each sample they run this small workflow, and what happens is that our provenance gatherer follows the wherever they are going and collects what's happening in all the meshes and all the things. And on the uncertainty quantification process, they have several samples and to do the iterative process. So they don't know in advance how many samples they are going to use. Like Drew mentioned, if they use a Monte Carlo simulation, they have to prefix, let's say, 1,000 samples and wait for hours. Whereas in this case, in the uncertainty quantification, you already do lesser samples. But in the adaptive uncertainty quantification, by querying provenance, they are aware of the behavior and they can finish earlier or they can see in a better way. So there are details. I'm not familiar with uncertainty quantification, but our specialists are very happy with what they have been getting from. In this case, we are not really changing the workflow, but we are finishing earlier and with a lot of provenance so that they can play afterwards with it. There are some workflows in bioinformatics too, and so just to conclude, there is a lot of room to work there. I believe that by having provenance being standardized by W3C, we have a lot of opportunities to have interoperability between what's being collected by the several tools. We'd like to work with other tools. We just have this high-performance engine, but no nice tools so that the user can interact. We have to help them a lot. So. These are some funding agencies, and our code is available if you like to try or ask us, and no nice interfaces, but a lot of real examples.
Okay, we actually do have time for a couple of questions. Yes. Yeah, so well, actually, before these guys come up with theirs, I do have one that I was thinking of as well. So I always think of the difference between dynamic workflows and being able to query the provenance at the end as a trade-off of one another. So when you're making it reproducible, that's really what it is, right? It's reproducibility. What do you save out if you were actually allowing a collaborator to reproduce your results using your method?
Well, the provenance that is stored, it's stored in the way of all other solutions. So in order to do the reproduction, you mean when we change the workflow in the... Yeah.
So you start with one workflow. Now you've changed it to another workflow, which is the second one that gets published out? Is that...
Actually, the whole history, it's available and it's there. Because if the person that wants to not reproduce but reuse that idea, if they get just the last part, it's not going to be exactly like this. But they have access to what happened in the beginning, in the middle, and in the end.
Oh, okay. All right.
We don't throw any provenance away.
No, I wouldn't think that you were. Okay, well, thank you very much.
Thank you.
Our last speaker is Dan Fay. He's with the Microsoft Research Connections team, and he's synonymous with Science at Microsoft because that's the blog that he has out there, in addition to running another blog. I don't know actually how he finds all the time. So he's going to speak to us on eScience in the cloud.
Okay, great. Perfect. Thank you. Cool. Good. All right. So again, for those who were here yesterday, I get the unlucky bit to be the last one right before the cocktails and the end of the day, right? So I'll try to go as quickly as I can to make sure that we're out there on time. But as Chris had mentioned, and I'm Dan Fay, I head up this area that we do in our science group. I want to get my timer here. And want to talk about some of the stuff that we do with eScience and what we've been doing, especially around some of the work around eScience and Azure in the cloud and taking advantage of some of the functionality there. So, oops. So, one of the things that we think about a lot when we look at not only the cloud, but any of the technologies that we have, and you've seen some of them from the different groups, the stuff that Drew was showing earlier this morning, some of the visualizations that Rob was talking about, all across the board here, all these visualizations and tools and techniques that we have as a company, as well as information, how do we use that in helping scientists actually do new ways of not only processing, analyzing, visualizing, but another key thing is communicating the information and the data to others. So it's kind of a theme through some of the things that we end up doing. Wanted to highlight this EOS article that Jeff Dozier, who's a snow hydrologist, had written around, it's in the theme of the fourth paradigm, but really taking advantage of how do you take satellite imagery information from that, as well as remote sensing data and local on the ground data, combine those together in analysis that you can actually get some more interesting information out on it. And it's a really good kind of synopsis of what we think about when we think and we talk about things like the fourth paradigm just in general, combining together many different types of data sets. One of the other things that we think about a lot, and this is a slide from some of our collaborators, and it really does hit why not only processing information, what's valuable, is that as you go up, as you process more of the data sets, and you make it more usable and more scientifically ready for others to consume, there's a value in there. All of a sudden, you're not having your grad students or those postdocs or the poor students here doing a bunch of grunt work, just getting data, pulling it all together, and actually trying to get to the science. So if you think back of some of the work you've done, how much of it was actually not even science related, but getting the data ready to do some sort of scientific work. And so this is one of the things that we look at, and it helps with the overall insight into the information. And so there's an interesting value in there, and how can you provide that to others, you know, as a service, or make it available, not just as purely the data, but as something that they could process against. And so when we look at that, we see that's where some of the benefit of cloud computing comes in. Not the fact that you're now just moving your computation from your server in your office to somewhere remotely. It's that you're actually giving somebody access or processing that information that they don't now have to do, right? Why should I actually have to rewrite a new algorithm when you actually have the best? And then the other thing we think about, though we don't know exactly the way to solve it, if anyone here has a good idea, would be, how do you reward folks that are great at the work that they do? If they're great at processing information and writing algorithms to process the data, that you know, you trust it, everyone in your domain trusts it, how can they be valued and actually given credit for doing that? That's a really key thing, because why have multiple people doing the same exact thing if somebody actually does a really good job on it? And we see this a lot with data sets, like people pulling it from NASA down, reprocessing the MODIS data sets in the exact same way every time. So that's one of the things we think about. You can kind of tell I get a little excited about that. This is some of the stuff hopefully most of the folks here know. We We kind of talked about it also during Drew's talk about the overall issues with data and especially the spaces of ecology. But it gets interesting because you start pulling together data sets of many different types and different scales, and how do you pull those together and actually compute those and also get some sort of meaning out of it. Everything from the model information, the output, if you have any satellite information coming down, or even sensor-based data. But even going back to historical information, which will never be as accurate as the current information you're getting because of measurement techniques and other calibration techniques that we currently use now. So, you have to put all those in there, and that's one of the things Drew was getting across this morning was how do you bring across the uncertainty in the calculations so that they propagate the whole work and not just one piece of it. Again, different types of data sets, how do you pull them together? This is really where especially in the ecology and the environmental space, these are the challenges that we kind of have been working with and some of the projects that we've been working on. So, but why? Why kind of go through all this and tell you about that? Well, it's really because there's a whole bunch of things. We heard about the provenance of it, but there's provenance really differently in the different domains, how they're being done. There's obviously data sharing concerns. Environmental data is really hard to get. People actually have to go out in the field and actually go and get it and collect it, get dirty, other things. You don't just sit back and have it flow in. So there's a real ownership to the information and data. And so how do you actually make sure it's shared in a good way and used in a good way, but also the person gets credit for it? And then there's a whole bunch of different types of computational tools. But the part that I actually really think that's interesting is what we put down here on the bottom, which is we actually think now science is really happening when you start bringing all these different data sets together and looking at them from a different kind of lenses across the scales of them. That's where you start finding out some of the more interesting information. So a lot of this is some background into one of the projects that we've done over a couple of years ago, which was called Azure Modus, which was a process, and this was originally done on Azure as it first was, which doesn't have all the functionality we currently do. But it was a service that we put up to help a researcher at UC Berkeley to do some evapotranspiration analysis over the whole globe at I think it was a 10-year continental scale at a more fine grain than had been done before. Previously, he'd been trying to do this on one machine. Would have taken forever to do it. So we were working with him on actually how you could pull this data set in, pull the tiles from NASA, from FTP sites, actually reprocess it because it comes in swaths. And so if you want to get to latitude and longitude and actually do it on and overlay it, you actually need to reprocess it and reproject it, go through that whole piece, then also do the computations on the values to get the evapotranspiration. And so there's some of the numbers here that we had previously done, and then get the result back to the scientists. So make this as seamless as possible. The challenge always is that there's FTPs stop, sometimes the files aren't there, so there's a lot of just issues just in general when you're trying to pull some of these data sets across and make them available. This actually, we're continuing on with a new project, actually with Young Rel, who's now was at UC Berkeley, is now in Korea. And so we'll continue forward on this, looking at how we can actually process more of this and in a way that makes it available to others. So when I look back on how we did this, it's what we call platform as a service when we think of cloud computing. And just as a quick background for folks that may not know the difference between some of them, there's the idea of infrastructure as a service. So where you essentially are hosting the machinery. There's the platform as a service where you're actually building a lot more of the functionality directly on there, but you let, in this case, cloud, or in this case, Azure, take advantage of everything. You don't worry about the OS. You don't worry about updates. You don't worry about anything in there. Or software as a service, where you actually have the service available for others to consume. And so these are kind of the three pieces that you'll hear in kind of the standard discussions around cloud computing. And I want to talk about a couple of those today, as well as describing a couple of the projects we've been involved with. Quick kind of marketing slide. Wanted to throw that in there. Azure really is about all these different services and pulling them together. So I'll cover a couple of those. Three main ones that I think are really applicable to folks here is the ability to use virtual machines. And I'll kind of go into that a little bit more, which is, it doesn't matter what types of virtual machines. There's a whole list of them that you can do. The ability to pull up get a website up and running really quickly, where again, you don't have to worry about managing the website except for your content, and you can actually have it scale up. And then things like cloud services, that platform as a service. How do I write bigger applications that run across the whole network, take advantage of more of the infrastructure? And this kind of exemplifies it a little bit better, where in the case of the VMs, you can have multiple virtual machines pulling from a gallery. One of them is, we already have predefined ones in Azure, where you can just pull those, get them up and running, and install your software and get going. So I'll show that in a minute. There's a Windows Server, there's Linux ones, there's all over the board there. There's also the ability to have your own user-supplied VMs. And so make those available not only for yourself, but for others to actually utilize. And I'll show something in a minute where there's a gallery we have out there as well, where you can actually post yours. Think of these as applications on the cloud, right? All of a sudden, it's up and running. I click it, and I'm running. I have the environment I need. I have everything running. I don't need to actually install much, because hopefully somebody who's working, who had created it, has all the connections and the links that you already need, and the software. The websites, you can have multiple of those running off the same server or singles. And then the cloud services, where we, for folks that are familiar with Azure, there's things considered worker roles as well as the web roles. And these are pieces that work on behalf of the service. So a lot of the pieces that we saw in the Azure Modus are the code that actually runs as both the web roles and also as the worker roles. So they're the part that actually crunch away for you. So just some of the pieces that are all involved. One of the things when I talk to people about what cloud is or about Azure, they don't realize the amount of services that are actually built on top. Think of it almost as if you had an operating system, what's also on there. So there's the compute pieces, where there's the cloud services, the VMs, and the websites. There's a whole bunch of other parts in there, from everything from a full SQL Server to blob storage, table storage is up there, and the ability to have virtual networking, so you can actually have connections from your local on-premises machines and work with the remote machines as if they're local. So you can actually burst stuff up and back. You can host data locally and actually have all the computations up remotely. Whole bunch of different types of functionality also there, but also then support for different languages. So one of the projects that's also been going on for about a year or so is this project, one of our guys actually, it's in our team now, Wen Ming has done, which is what's called Weather in the Cloud. It's essentially bringing the WRF model and some of the other functionality and implementing it natively just right onto Azure. So make the weather computing almost like a service. And so you can actually go, if you have your laptop open and are doing email or want to taking notes, you can go up to the weatherservice.cloudapp.net, the URL up there, and you can actually see some of the pieces that have already been done. But it ends up using a lot of the platform as a service and some other functionality as well let me bring that up. To allow you to run this as a service. So hopefully this one actually finished. So I actually started this one earlier. Okay, so it's starting the animation step. I started one right now to go through what the weather forecast would be for Sao Paulo during this time frame. It gives you a 3-day weather one. You can pick the area that you want and then actually have it run. Because we're running on a small node right now, it takes about probably about 5 hours to execute. Because it actually goes out, pulls in the data, executes it, and then does the animations on it. But we also then have all the information on there. Actually, let's go to a smaller size. Okay. Which has all the log files, what's actually happened during the computations, and all the whole kind of the data in there. And you can also pull down the logs themselves. What'll occur, that one's not done yet. I'll take a look at this one. We'll come back to this in a second. If we go to the gallery, you can see a whole bunch of other ones that have already been computed. And so we have the imagery up there. It'll do the, that's the California one. We can go in and actually see the animation of, in this case, it's the heat, and play it through as well. So the temperature during that time frame, and it'll start rotating around. Oops. But what's interesting about this is all of a sudden we've taken a wharf model running and actually put it up as a service that you can actually just run, query again, actually execute it, start it running, and we know about how long any of these should take, from pulling the data sets down, executing the wharf model, and then performing the animations on them. Hopefully there's not going to be any snow. Oh, that's good for this time of the year. But also you can also go through the precipitation on it if there was any going on. And if I wanted to create a new one, it's pretty easy to actually just select a location and then just have it go off and execute. So part of the idea was how we could make it easy, but also the real key piece in this whole application was how could we take off-the-shelf code and actually very easily get it running in the cloud as a service and make it available. So let me switch. Good. This one, since it's using wharf model, uses just standard MPI. Didn't change anything in there, and it does the detailed forecasting. There's a whole bunch of also data sets on there. But again, feel free to go try it out. It's we just have it up there running and running. Either my eyesight's going bad or this is really blurry. But that kind of shows a snapshot before of all the ones that have been done in those areas. And so then you can actually go in and see what's already happened, look at it, typical kind of website interactivity. So what's actually kind of happened in this area? So we actually use what's our HPC scheduler for our high performance computing on Azure. We do have the scheduler kick off the compute jobs. Those are written as both as worker roles within Azure. Start the processing, which goes out to NOAA, pulls down the latest information data sets for that area, actually does the computations, and stores out into the blob storage within Azure. And then you can keep doing that for more and more data sets. So to even increase it, you can actually create use the management pieces that are already in there to increase the size of the VM you want to use or the roles that you want to use. So it makes it a very nice interface to deal with. To do some of this work, what we ended up doing was using another feature within Azure, which is the ability to use multiple languages against it. So not only can you use some of the standard languages that Microsoft supports under .NET, C#, some of the other ones, but also there's a bunch of other support for, Node, there's the Python, Java. And so within this, we actually use some of the support for Python. And Dennis asked earlier, folks used it, Python. One of the things that's really useful within Azure and within the product team that they've done is have native support within Visual Studio. So have a real IDE for actually creating Python applications. And so you get advantage of a lot of the IDE and the processing that you have in there to take advantage of for doing not only IntelliSense and some of the other work that most people enjoy in a IDE, but also debugging and some of the other analysis in there. So we end up, and within there, there's also the support for all the traditional technical and scientific computing support. So if you do Python type computing, take a look at the PTVS, and that's actually installed within Visual Studio. Very useful. The other key piece that Dennis also mentioned was kind of the IPython notebook. So that's an extension there. You can create these and they run within a virtual machine. And why that's kind of useful is that all of a sudden you can get this up and running, have it running in your own VM, and control it however you want. So, like as I mentioned earlier, the virtual machines support not only Windows but also Linux, and you can do it have the virtual networking to actually interact with it directly as well from a local site. So you can have these running remotely, and they look like they're on your own network. So it's a real kind of benefit in there. There's two different type of depots that you can pull virtual machines from. So the one that's built into Azure allows you to pull in a bunch of standard ones. There's Windows Server in there. There's a whole bunch of Linux distributions, SQL Server distributions. And then there's a community-based one from one of our subsidiaries called OpenTech. And they have a whole bunch of also virtual machines that people have done from the community, package them up, and make those available. So if you had a specific image or that you wanted to actually the community to use so they could just get up and running, or your own application, this would be a place you could put it. Get it up, running very quickly. So somebody could use it rather than having to do all the installation. Yeah. So there you see a couple of these that are on there already. And then also the Azure SDK for Python is available too, so we have native support within there. So one of the things, like I mentioned, Azure has a whole bunch of these building blocks in there. I only showed in the weather one, us using a few of those, but there's a whole bunch more, both on logging in, the identity piece, mobile services, the load balancing, storage, and on goes down the line. And a lot of it's also available like through the SDK, and all the tools and libraries are available as open source on GitHub. So you can go out there and actually see what's going on within the code. Yep. So let's skip over there. So I just wanted to kind of cover some of the projects that we've been kind of working on there. This, from where we started with the Modus Azure to where we are now, it's so much easier to even get up and running. We can deploy an application in no time. You can create a website, copy it up, and be up and running within minutes. And so I have a whole bunch of links here to some of the resources, both for students. There's the resources up for how to get some of the cycles and some of those. The information on Python, the depots. For faculty, if you're interested in using any of this in your courses, there's grants that are available from another part of our organization that will give grants for 6 months to a year for you and your students to actually execute code on and to run. So think of it as a virtual lab. You don't actually have to worry about those machines locally. So very kind of useful. The other thing you may be interested in as well is, put it at the bottom as well, there's, we have the flyers out there. If you're interested in, from a faculty point of view, there's a kind of a RSVP. It's down there. If you send it to Azure U at Microsoft with your information, they're collecting a community of folks on the faculty side, and so folks that want to share information. And then there's another pamphlet that has a whole bunch of the information on Azure as well, how to get up and running, and what resources are there for both the students and faculty. So. Just, you know, as Tony had on his slide earlier today, the future is, you know, coming type one. It's actually now. The clouds are out there from us, from other vendors. And in our case, Azure, it's available. We'd really love to see people test it out and use it, especially on the science side. And myself, Dennis, and the rest of my team are always willing to try to help and see where we can help on the science side to help you solve some of those problems that, you know, people run into, not only using technology, but to solve the science, because that's, I think, which is really key. So thank you, and I finished early, so you guys will be able to get out there for cocktails early enough. Thanks.
It sounds like you're making a lot of work for Dennis and I.
Of course.
Do we have other questions from the room? Yes?
No, they're not going to leave. I told them cocktails and demo fest. Yes.
I have a question. Maybe it's not just for you. It's maybe for Microsoft approach to big data. In Force Paradigm by Jim Gray, it's clearly stated that in big data cases, it's the process that should go to the data, not data that go to process. But I'm seeing that almost all products are fetching data, not going to data.
You're right. One of the challenges, well, I should say yes and no. There's two pieces kind of in there. So it's very hard to break people's habits about compute and data and pulling the data to the compute. So Jim's whole thinking on this was you need to move the compute to the data because at a certain point you can't move enough data to actually get it there, right? The bandwidth just isn't there. And yes, we can keep increasing bandwidth. Problem is the data just keeps increasing, right? So it's you need to balance it. So the whole idea was you moving the computations to there. As I mentioned, it's very hard to break people's mindset and how they usually go about processing it. So everyone is used to this model. And so that's why you see it reflected in a lot of the functionality. What the cloud does enable you to do is actually have a pot of data that is actually more local than you going and pulling it all the way across the world. So you are essentially, a lot of times in this case, moving it at least into the same building to do the processing and not moving the big bit of data down locally and processing on a smaller machine. There are some other technologies, though, that do some of the more the data on the and the computation together. One of them didn't talk about here today, but we've done with some other projects is some stream processing one, where as the stream's coming in, you're actually continually processing on it as it's essentially going by. And so there's a SQL Stream Insight product that we have. We use that at a project in USC looking at traffic data. And so it allows you to do the analysis more instantly because you're looking at this data. One of the key things, and I've been looking for some collaborators to try this out, because I actually do believe this is, would be useful. It doesn't need to just be on real-time streaming data. It can be on historical information and data. So you can actually have it process, put the box, the node, as close to the disk as possible, and actually have it process on that, much the way, say, an advanced grep might work, and you're executing it, but dealing with it in a spatial and time constraint type way. And so your latency is from the disk to the computation, which could be right next to it, and not across the network or anything. So it could actually essentially be the front end there.
In this case, you are paying the cost of the application, let's say, if there are some multiple processes needing same data.
Are you talking about in that case, in the Stream Insight, or in the case of just?
In the usual case.
Oh, so in that case, what's the benefit is that most of the time everyone's caching anyways in the cloud side, so you're actually speeding up for the next person. Yeah.